This is 5.6, part 2. So we were looking at L'Hopital's rule, and I'd like to do another example. Let's see which one. Okay, let's do this one. The limit as x approaches 1 from the right of 1 over natural log of x. By the way, this needs to be a one-sided limit like the one before, because that tangent or cotangent that we're dealing with has a vertical asymptote, and so we can't approach it from both sides. It has to be a one-sided limit. So the problem itself necessitates that being a one-sided limit. And you can only approach natural log of close to 0 from the right. That's another reason. Anyway, now natural log of 1 by substitution is 0. 1 divided by 0 goes toward infinity. And 1 over close to 0 goes to infinity as well. So we have infinity minus infinity, which is an indeterminate form. So what we're going to do with this difference, and this is pretty standard when you get an indeterminate form that is subtraction, is I mentioned early on in the last session, you're going to want to find a common denominator and actually do the subtraction. So I'm writing this so that I'm leaving room for what I'm going to need to do to get the common denominator. Okay, so the common denominator is the product of those two denominators. So the first fraction is lacking the x minus 1 as a denominator factor. So I'm going to multiply by that form of 1 to make it have the same denominator as the other one. The second fraction is missing the ln of x as a denominator entry. So I'm going to multiply by this form of 1 so that they have the same denominator. And of course, you know, once you have the same denominator, you simply add or subtract the numerators. And so this will be x minus 1 over our common denominator minus ln of x over our common denominator, and when you subtract the numerators, there aren't any like terms, so there's not a lot of subtraction involved as far as combining like terms is concerned, and you get this fraction as a result. And what we're hoping at this stage is that this becomes, as the limit of a fraction, we hope it becomes 0 over 0 or infinity over infinity, so that we can actually use L'Hopital's rule. Okay, so let's see what happens here. When we substitute in 1, 1 minus 1 is 0, natural log of 1 is 0, 0 minus 0, that's headed towards 0, and 1 minus 1 is 0, and natural logarithm of 1 is 0. 0 times 0 is 0. So this is actually a candidate for the use of L'Hopital's rule. And again, notice that every time I'm using L'Hopital's rule, I'm indicating the change to this new thing because of L'Hopital's rule by writing LH over the equal sign. All right, so the derivative of x is 1, minus the derivative of 1 is 0, minus the derivative of ln of x is 1 over x. And in the denominator, that's a product, so I have to use the product rule. First function times the derivative of the second function plus the second function times the derivative of the first function. Okay, then let's do a little bit of algebra. move this up a little bit so we can see what's going on a little bit better. Let's see. I think what I'm going to do algebraically with that result is clear the equation of all the little fractions by multiplying this fraction by x over x. That'll just make it cleaner looking. So x times 1 is x, minus 1 over x times x is 1. X minus 1 times 1 over x times x is x minus 1 times 1, which is x minus 1, plus x times ln of x. Okay, so try substitution. 1 minus 1 is 0. 1 minus 1 is 0, plus 1 times 0 is 0, so that adds up to be 0, and so we can use L'Hopital's rule again. Remember, we can use it repeatedly. As long as we're getting 0 over 0 or infinity over infinity, you can use L'Hopital's rule. Okay, the derivative of the numerator leaves 1. The derivative of the denominator leaves 1, minus 0, plus the derivative of x, ln of x. So that's going to be first function times the derivative of the second function plus the second function times the derivative of the first function. And let's clean that up a little bit so we can see what is what. Okay, x times 1 over x is 1. 1 plus 1 is 2. Plus ln of x times 1, of course, is just ln of x. So now try substitution. Ln of 1 is 0. 1 over 2 plus 0 is 1 over 2. Of course, that's 1/2. Now, this one was not something that we set equal to y and have to do anything with. This is a straight up limit. We've just been algebraically changing things and using L'Hopital's rule to change things. So that is actually the answer to our limit question. Now, wow, what happened? I don't know if you see that like I see it, but all of a sudden that just looks really wonky. I think that happens sometimes when I move the screen. At least that looked like a blob where I just erased. So I'm going to try to fix that and make it look correct. Equals 1/2. All right. So we know the indeterminate forms that I wrote out before. Here are some determinate forms that are easily confused, where you might think, oh, I have no idea what that equals. That must be indeterminate. I've got to use techniques like what we've been talking about. Actually, you don't. For the determinate forms, you don't have to do that. For example, infinity plus infinity is headed towards infinity. No ambiguity there. Negative infinity minus infinity is headed toward negative infinity. That is not an indeterminate form. It's actually going to head toward negative infinity. 0 to the infinity is going to lead us toward, I should put arrows here, lead us toward an answer of 0. And 0 to the negative infinity takes us toward positive infinity. So let's contrast that with the indeterminate ones so that you kind of have a side-by-side comparison of them. Indeterminate ones, 0 over 0, infinity over infinity, where one or both of those could be negative infinity, infinity minus infinity, 0 times infinity, 0 to the 0, 1 to the infinity, and infinity to the 0. The ones on the right are indeterminate, which means we're going to have to do something like we've done in this lesson to change it into something where we can evaluate it, or use L'Hopital's rule to evaluate it. Please remember that we can only apply L'Hopital's rule to the first two. So if we don't have that form, we can't do L'Hopital's rule. We can sometimes adjust, like we've seen in this lesson, so that it becomes that, but until it's that, you can't use L'Hopital's rule. So here's something that will, if you're not paying a lot of attention to, you may see this problem, e to the x over x, and you're thinking, oh, that's infinity over infinity, because you're used to thinking about as x approaches infinity. But be careful, this is not x approaches infinity, this is x approaches 0. And so this heads toward e to the 0, which is 1, over infinity. So this is sort of what we're thinking in our heads. And any constant divided by something that's headed toward infinity, that's 0. What you would not want to say, what I'm about to write as false, is that would equal the limit as x approaches 0 of derivative of the numerator over derivative of the denominator. E to the 0 is 1, 1 divided by 1 is 1. That's false. Everything I just wrote in pink is wrong. So be careful about jumping to a false conclusion and just think everything you can take derivative of the numerator, derivative of the denominator. And no. If you don't meet the hypotheses of L'Hopital's rule, you can't do it. And the hypothesis of that is you will get either 0 over 0 or infinity over infinity to be able to use L'Hopital's rule. So I do beg that you use caution, and I will see you in class.